Good morning, class. Wow, it's not a lot of people are on time today. All right, well, I'm going to get started because I want to get through my lessons and start the weekend. So, hopefully people will show up. All right, so after this lesson today, I want you guys to go to the Zoom room as quickly as possible because I just want to review one more time what we're going to be doing once we return to in-person school. So, yeah. Okay. So this is AP Physics 1, 16th, and this is period 4. All right, so we're continuing to talk about experimental physics. And so the first thing I'm going to talk about today is energy. All right. Energy, we have three different types of energy that we've discussed most frequently. Okay. So one of the types is kinetic energy, which is the energy of motion, 1/2 mv squared. We talked about gravitational potential energy, which I'll call maybe U sub g, and that is mgy. And then we also talked about elastic potential energy, which is 1/2 kx squared. So what are some different experiments that we could do with energy? Well, one common experiment that we could do is we could have a ramp. All right. So we have a ramp, and then we have an object that is on the ramp, and we let it slide down the ramp like this. Okay? And then what we do is we measure its initial height, and then we measure its speed once it gets to the bottom. Okay? And what we do is we start out the object at a couple of different heights. Okay? And we measure its final speed at the bottom in each case. So maybe y0, y1, y2. And at each different height, we get a different speed at the bottom. Okay? So we get a data table of height versus speed. Actually, we will probably do this experiment eventually when in in-person class. So, yeah. So what is the theoretical relationship between these variables? So if we apply the equations of physics, what should be the relationship between these variables? Well, if we apply conservation of energy, you can see that we start out with gravitational potential energy and we end up with kinetic energy. So if we say initial energy equals final energy, that's the law of conservation of energy, then that means that the initial energy is gravitational potential. The final energy is kinetic. All right. We cancel out the mass, and we get that I could also multiply both sides by 2. All right. And then we get 2gy equals v squared. All right. So this is the theoretical relationship between the variables. Okay. So we can see that we sort of naturally have v squared appears in the equation. So probably what I would want to do if I was analyzing this data is I would want to convert not to a table of y versus v, but instead I would make a data table. I would then take these numbers and square them, so I have a y versus v squared data table. Okay, because my model equation of applying the equations of physics, I get v squared in that equation. So, and then what I would do is I would graph v squared on the horizontal axis and v squared on the vertical axis and y on the horizontal axis, okay? So if I do that, this is a really important skill, okay? So make sure you're following. What you want to do is once you decide what you're going to graph, you want to replace the thing on the vertical axis with y. So I'm going to replace v squared with y. And on the horizontal axis, I have y, so I'm going to replace y with x. Okay? So it's really important that you make these substitutions because that's going to tell you what the slope means. Okay? So I can see that the number multiplying x is 2g. So comparing this with the standard equation of a line, y equals mx, I can see by comparison that the slope is 2g. So this data should look like a line with slope 2g. So in other words, the slope should be about 20 because gravity is 10 on Earth. If you did this experiment on another planet, it would be a different slope. Okay, so that's really important that you understand if you have a graph, how is the slope going to be interpreted? Okay, and the way you do that is you apply the equations of physics to get a relationship between the two variables, and then you see what is multiplying x. Essentially, that's the slope. All right. Let me give you another possible experiment involving energy. Okay. This one we might actually do. I think we'll probably do this this experiment in person. Probably do both of these experiments in person. So we could have a spring. All right. And there are so many different experiments we could do with this one. It's crazy. We could do a spring, have a spring here, and we're going to compress the spring an amount A. All right, so the spring is compressed from its natural length. All right. And then we let the spring decompress. and we launch the mass. Okay, so that's an experiment we could do really easily. And so there's so many different things we could vary here. We could compress the spring the same amount each time, and then change the mass of the object so we could launch different things. Or we could keep the same thing and compress the spring by different amounts. All right. But in any case, we're going to measure how fast is it going. All right. So I'm going to say that we keep the mass the same, but we compress the spring by different amounts. Okay. So we would get a data table where we have different amounts of compression, and then we see how does that affect the speed. Okay. So what we want to figure out is what should be the relationship between these variables. Okay. What should be the relationship? Okay. And so again, we're going to apply conservation of energy. All right. So in this case, instead of starting out with gravitational potential energy, we start out with elastic potential energy. So initial energy equals final energy. This becomes, the initial energy is 1/2 Ka squared, and the final energy is 1/2 mv squared. So I can see that both sides of the equation have 1/2, so I'm going to cancel those out. And then I'm also going to divide both sides by m. Okay, so if I do that, I get k over m times a squared equals v squared. All right. And then I could take the square root of both sides. So if I take the square root of a squared, if I take the square root of v squared, then that's going to give me square root of k over m times a equals v. All right. So notice how naturally in the equations of physics, I get a and v. Whereas here, I got y and v squared, so I had to graph v squared on the axis. Here, I naturally got a and v, so I don't have to do any squaring or anything to get a linear relationship, okay? So what I'm going to be doing is I'm going to be graphing v on the vertical axis, and I'm going to put a on the horizontal axis, because in my equation of physics, I naturally got a to the 1 power and v to the 1 power in my equation. Okay, so I have v on the vertical axis, so v is kind of like y, and then I have initial compression, a, on the horizontal axis, so a is kind of like x, so I replace a with x, and then the thing that's multiplying x is square root of k over m. So what that means is that this relationship is a line with a slope of square root of k over m. All right. So what we're doing is we're learning how to interpret the slope from your experiment. Because usually what you do in physics is you collect data, you make a graph out of the data, and the slope means something, okay? Now, what would you say if this data didn't look like a line? Maybe it looks like this. In fact, I think if you actually did the data, it would probably look like this, okay? So this means that the data deviates, it's different from what you expect, okay? And if the data is different from what you expect, then that means that your assumptions are wrong, or it means you discovered new physics. In this case, I would say that probably your assumptions are wrong because this relationship is assuming that there is no friction affecting the motion of the block. If we included friction, if we included friction, then friction is going to have the effect of reducing the speed of launch below what we expect. So see how I drew this? My dashed line is curving below what I actually expect. And that's why I drew it that way, because I think that probably the block will come out slower than what I expect because of friction. Okay, so this is probably what will actually happen. It's probably the outcome of the experiment, probable outcome. So again, if you don't see the data that you expect, it could mean that you discover new physics, or it could mean that there's something that's not being accounted for in your analysis of what you should get. All right, so probably friction is going to be important, and so that's going to cause this graph to curve below to lower speeds. Okay, and in fact, I would probably expect the same thing in this graph as well. The speed, when it gets to the bottom, is going to be lower than what we might expect because of the presence of friction. It's impossible to completely get rid of friction. So I would expect that the actual data will curve below this line. All right. It'll have a slope of less than 20. So we apply the equations of physics. We get a theoretical relationship between the variables. And that tells us what we should graph and how the graph should be interpreted. And then we actually do our data. We may or may not get something that matches what we expect. If we get something that doesn't match what we expect, we try to explain it, okay? So we try to say, all right, friction is probably reducing the speed. Or it could be new physics. Probably not at the level of AP Physics 1. You're not discovering new laws of physics. The next thing I want to discuss is momentum. So the equation for momentum is P equals mv. All right. P equals mv. And one of the things about momentum is it is conserved in collisions. So in collisions, the initial momentum, the total initial momentum, okay, is equal to the final total momentum. Okay? And when I say the total momentum, I mean the momentum of all of these objects summed up. Okay? So here's a simple momentum experiment that you could do. All right? You could have, here's a floor. You have a block that is sliding along. So maybe this block has a mass m1 it's sliding along with a speed v initial, and you measure that speed. There's another block that is initially at rest, and the first block collides with the second block, and the two stick together. And then afterwards, they start sliding together to the right. Okay. So there's a lot of different things we could do. We could vary the masses, but I'm going to assume that we vary, because when we're doing an experiment, we always change variables and see how that affects the outcome. Okay. So we could change this mass and see how it affects the outcome. We could change this mass and see how it affects the outcome. I'm going to say that we changed the initial speed, and we saw how that affects the outcome. Okay? So we change the initial speed, and we see how that affects the final speed. Okay? So we slide block 1 into block 2 with a bunch of different speeds. We measure that initial speed, we measure the speed after, and we get a bunch of data points. Okay? So this is called a completely inelastic collision when they stick together. So theoretically, so when I say theoretically, I mean according to the equations of physics. Okay. What should happen? What should be the relationship between these variables? So I would say initial momentum equals final momentum. Then the initial momentum is carried only by block 1 because block 1 is the one that is moving. Block 2 starts out at rest. So my initial momentum is m1 v initial. Afterwards, both blocks are moving at the same speed. So they're acting like one big composite block. Okay? So afterwards, the mass that's moving is m1 plus m2. And they have a speed v final. I'm going to divide both sides by m1 plus m2. So that's going to give me m1 over m1 plus m2 times v initial equals v final. Okay? So I can see that there is sort of naturally a linear, these v0 appears to the first power, v final appears to the first power. So that's the graph that I'm going to make. Okay? So I don't have to square anything or do anything like that. I would just graph v final on the vertical axis and v initial on the horizontal axis. Okay? So let's see, what should that relationship be? I have v initial is acting like x because it's on the horizontal axis. V final is acting like y because it's on the vertical axis. And I can see that the thing multiplying x is m1 over m1 plus m2. Okay? So this graph, if I graph this data, theoretically, it should be a straight line. And the slope of that straight line is related to the masses of the objects in the experiment. Okay? So again, usually what happens is friction plays a role that has the effect of reducing velocities below. So as time goes on, the velocity gets more and more reduced. So I would expect something like this. So, a cool thing you could do is you can actually put these masses on a scale, and you can calculate this ratio. So you can get an expected slope. So this is the expected slope, and then maybe your actual slope is different from that. Okay, and then so it's up to you, the experimenter, to decide why, or to try to explain why is the actual slope less than the theoretical slope. And a lot of times the answer is friction. Okay, if you got that it's less, it's probably friction. If you got that it's more, if your actual slope was like this, that's kind of more interesting. It's like sort of like energy is being introduced into the system somehow. Or maybe your scale is not correct, something like that. So another experiment you could do with momentum that's very common is you have two masses, M1 and M2, and you kind of like put a compressed spring between them. Okay, so initially the system is at rest. Okay, and then you let the spring do its thing. So the spring goes wow, 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 like that, and launches the masses in opposite directions. So the spring does its wow, 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 wow thing, and it launches M1 this way, and it launches M2 this way. Okay, and so maybe what you do, so the more you compress the spring initially, the higher these speeds are going to be. So maybe what you do is you compress the spring different amounts. And then you see what is the relationship between these two speeds. So you measure what is the final speed of the left object and what is the final speed of the right object. This is the right object. Like that. Okay? And so you see what is the relationship between these two final speeds when you compress it different amounts. Okay? So the purpose of the different amounts of compression is purely to get different launch speeds. Okay? So theoretically, what should be the relationship? Well, using conservation of momentum, P initial equals P final. The initial momentum is 0 because the system is at rest. Momentum is mass times speed, so if you have no, or mass times velocity, so if you have no velocity, there is no momentum. Okay? So the initial momentum is 0. The final momentum is the momentum of object 2 plus the momentum of object 1. So object 1's final velocity is, or final momentum is M1 V1 final. So I should call this V final 1 and this V final 2. And then object 2's final velocity is m2 v2 final, so that's its final momentum. So then what I can do is I can subtract this over, and I get minus m1 v1 final equals m2 v2 final. All right? And then I divide both sides by m2. I get minus m1 over m2 times v1 final equals v2 final. Okay? So this is the data that I have collected. So I'm going to make a graph of v2 final, okay, versus v1 final. Now, how does that graph look? Well, I can see if I put v2 final on the vertical axis, then that is acting like y. And I put v1 final on the horizontal axis, so that is acting like x. And I can see that the thing that multiplies x is minus m1 over m2. Okay, so the slope, masses are always positive, so the slope is going to be negative. And I would expect that slope to be negative m1 over m2. Okay, so that is the theoretical slope. So I expect a linear relationship and I expect a certain slope. That doesn't mean I'm going to actually get that, because there can be other things. Most common in this class, it's friction, that affect the final speeds and make them different from the theoretical value. Because a lot of times in physics, we consider idealized situations where there is no friction. But the reality is that friction is usually there. Okay, so that's my lesson for today. And I'm going to see you in the Zoom room, and I'm just going to go over one more time what the plan is for next week. Okay?